Hey everyone! Welcome back to the channel. In this video, we're kicking off a full MCQ breakdown series for AS level physics. And we're starting with a classic topic that catches a lot of students out: moments. We've got a 30 centimeters ruler balanced at its center, the 15 centimeters mark. There's a 50 grams mass at 23 centimeters on the right, and a 20 grams mass at 11 centimeters on the left. The question is, what mass do we need to place at the 7 centimeters mark to restore balance? This one often trips students up because of how we calculate the perpendicular distances from the pivot. So, let's break it down step by step. Usually, when we do calculations on physics question, we have to make sure all the values are in SI unit. Distance should be in meters, and masses should be in kilogram. In this question, since all units are consistent, we can skip SI conversion without affecting the result in order to save time. Same for the distance, as all of them are in centimeters. For moments, questions. Whenever the question mention about the system being in equilibrium, static, stationary balance, all these keywords mean we have to use the principle of balancing all the clockwise and anticlockwise torques around the pivot. So recall the formula for moments. Moment equals to force times perpendicular distance. Force in this system refers to the weight of each mass. How about the perpendicular distance? Perpendicular distance is the distance between the force and the pivot, which is in the middle of the ruler in this case. The most tricky part in this question is about the perpendicular distance. As the question didn't directly tell us the distance, it stated the mark that each mass is at. That means, for the mass that has been placed on the 7 cm mark, the perpendicular distance of the mass from the pivot point is actually 15 cm minus 7 cm, which result in 8 cm. Apart from the perpendicular distance, we also need to determine whether the mass is creating a clockwise or anti-clockwise moment about the pivot point. The two masses on the left of the pivot create an anti-clockwise moment as they tend to rotate the left side down, while the mass on the right of the pivot creates a clockwise moment as it tends to rotate the right side down. Now, we could do the actual calculations. Let M be the mass you should place on the 7 centimeters mark. Sum of all clockwise moment equals to the mass 50 grams times the difference between 23 and 15. Sum of anti-clockwise moment equals to the sum of the moment of the two mass on the left of the pivot. To restore balance, two moments must be set to equal, and by solving the equation, we obtain M equals 240. So the answer is B. A 40-gram mass should be placed to restore balance of the ruler. Remember, the key here was calculating those perpendicular distances correctly from the pivot. Great job if you got it right. Now, let's build on that and tackle the next question in this moments series. Let's move on to the next question, on moment. A square shop sign. Mass 2.4 kilograms, side 0.86 meters, hinged along the top edge, hanging in equilibrium at 15 to the vertical. What's the moment torque about the hinge due to the weight of the sign? Firstly, consider the center of mass of the sign. Since it is a uniform square plate, the center of mass where the weight effectively acts is at the geometric center. So distance from hinge to center of mass would be half of the sign length, which is 0.86 divided by 2 equals to 0.43. That's the straight line distance along the sign from the hinge to the center of mass. Recall the formula for moment. Moment equals to the product of force and perpendicular distance from pivot to line of action of force. Here, the force is the weight mg acting downward at the center of mass. The pivot is the hinge. So, we need the perpendicular distance from the hinge to the vertical line of the weight. In the right triangle formed, the hypotenuse is 0.43 meters. The angle with vertical is 15. So, perpendicular distance equals to 0.43 times sine 15. Force equals to the weight of the sign 2.4 times 9.81. Finally, we multiply force and perpendicular distance together to obtain moment, which is 23.52 times 0.111. The moment is 2.6. The answer is option A, 2.6 Newton meter. Alright, moving right into our next moment-related MCQ multiple choice question. This question is from the same paper of the last question. This one shows a simple couple, two equal and opposite forces separated by a perpendicular distance. The question is, how is the torque of the couple calculated? First of all, understand the basics. A couple is a pair of equal forces acting in opposite directions on an object, but not along the same line. This creates rotation without net translation, pure torque. In the diagram, you see two forces, one up, one down, separated by that perpendicular distance. Assume each force has magnitude F, and the distance is d. Remember, torque is the same as moment. For a single force, torque is force times the perpendicular distance from the pivot to the line of action. For this question, there are two forces. So, the total torque from the couple is the sum of the torques from each force. We pick a pivot point for couples. It doesn't matter where, but let's imagine one in the middle, for simplicity. For the left force, the perpendicular distance is half of the perpendicular distance d. So torque equals F times 0.5 d, and it causes clockwise rotation. For the force on the right, the perpendicular distance is also 0.5 d, so the torque equals to force times 0.5 d, and also in clockwise direction. As both of the torque is causing a clockwise rotation, the total torque of the couple would be sum of the two torques, which is 0.5 Fd times 2, which is Fd. The total torque matches with option B. Perpendicular distance between the forces times magnitude of one of the forces. Here comes to our fourth moment question in 2025. A non-uniform bar PQ is 50 centimeters long and weighs 200 Newton. A 400 Newton block sits right at the center. On top of it, the bar rests horizontally on the ground at both ends P and Q. Now, we apply an upward force of 360 Newton at end Q, just enough to lift Q off the ground. The question is, what's the distance from the center of gravity of the bar to NP? This one's tricky because the bar is non-uniform, so the center of gravity isn't at the midpoint. Let's solve it, step by step. As the force at Q is just sufficient to lift NQ, meaning the normal reaction at Q is now 0. The entire system is on the verge of rotating about point P, so point P becomes the pivot. All torques must balance about P for equilibrium right before lifting. We determine all the forces in the system and define their direction of moment. Weight of the bar is 200 Newton downward at its center of gravity. We label it as G with a distance d from P. And this is what we're finding. Block's weight is 400 N downward at the center, 0.25 meters from pivot P. The upward lifting force is 360 Newton with a perpendicular distance of 0.5 meters from pivot P. Since it's in equilibrium just before tilting, the total clockwise moment about P equals the total anti-clockwise moment about P. We calculate each moment about P by the formula moment equals to force times perpendicular distance. Sum of clockwise moment equals to the sum of moment caused by the block and the non-uniform bar. Sum of anti-clockwise moment equals to the moment caused by the uplifting force 360. So the sum of all clockwise moment is 100 plus 200d, while that of the anti-clockwise moment is 180. For equilibrium, these two moments must be equal, so we have 100 plus 200d equals to 180. So the center of gravity of the non-uniform bar PQ is 0.4 meters from P, meaning it's only 10 centimeters from Q. So the distance from the center of gravity to NP is 0.4 meters. Option D is the answer. This is a beautiful example of how non-uniformity shifts the center of mass and affects torque balance. Here it comes to the last question, on moments in 2025. A problem on Seesaw. We have child X, mass 20 kilograms on the left, child Y, mass 15 kilograms on the right, sitting on a uniform plank of mass 7.0 kilograms. The pivot is exactly at the midpoint, and the whole system is horizontal and in equilibrium. Which statement about the weight of the plank is correct? This one tests whether you really understand how a uniform plank behaves in torque calculations. The plank is uniform, so its center of mass acts exactly at the geometric center, which is the midpoint, exactly at the pivot. Let's look at the options one by one. Option A states that the weight of the plank can be considered to be acting at its midpoint. As the plank is uniform, the weight acts at the center of mass, which is the midpoint, and since the pivot is there, this is exactly how we treat it. So this is a correct statement. Option B, the weight of the plank is causing an anti-clockwise moment. This is not true because the perpendicular distance between the center of mass of the weight and the pivot is 0. It causes 0 moment. C states that the weight of the plank is causing a clockwise moment. Similar to option B, the weight of the plank causes 0 moment, so the statement is incorrect. Option D, the weight of the plank equals the force on the plank from the pivot. The pivot force is actually supporting the total weight of all the objects. It is much larger than plank's weight. So, option D is also wrong. The correct answer is option A. In this video, we have analyzed 5 multiple choice questions on the topic moment. Here's a wrap on the topic. We have to choose the right pivot point, especially when something's just about to lift or tip. Calculate perpendicular distances carefully. Sin theta for tilted stuff. 0 when force acts through the pivot. For uniform objects, weight acts at the center of mass. For non-uniform, it's offset, and that changes everything. Net torque equals 0 for equilibrium. And add up those moments properly. The sum of clockwise moment equals to the sum of anti-clockwise moment. If this series helped you, please smash that like button. It really helps the channel. And if you haven't already, hit subscribe and turn on notifications so you don't miss the next series. Maybe forces and fluids, waves, or electricity next. Let me know what you want. Thanks so much for watching all the way through. You're awesome. Keep practicing those torques. Stay curious, and I'll see you in the next video.